And in this case, it might print to the screen, "Oh, hi, world." Well, now, how do you actually get from all these zeros and ones to useful data? Well, it's actually relatively straightforward. So I'm just going to open up, again, a simple little text document here, just so we have something to type with. And it turns out that if I want to represent the number we humans know as 0 in binary, otherwise known as base 2, well, the world has decided that 0 for a computer means 0 to a human. So pretty simple. Well, if we want to do the number 1, it's actually pretty simple. Unfortunately, now we're out of digits, right? The alphabet is only so expressive. So now, using only zeros and ones, we have to somehow be able to encode what we humans know as the number 2. Otherwise, this is going to be the most useless computer ever if the best it can do is count up to 1. Surely we can do better. So what can we do? Well, much like in the real world, when you need another digit, you add 9 plus 2. Well, 9 plus 2, what do you do when you kind of did that in grade school? You you carry the 1, right? So you get another column. We can do the same thing here. So to represent the number 2, why don't we do something like 1, 0? And the number 3, 1, 1. And now just to make things line up prettily, let's just assume that every number in the world uses 2 bits. And a bit is just a 0 or a 1, binary digit, bit. So now, using zeros and ones, I can represent what we humans think of as 0 and 1 and 2 and 3. And take a guess. What's the number 4 going to be represented with? Yeah, 1, 0, 0. And now I can go back and clean this up. Much like in the real world, you can have as many zeros to the left of some number. It makes no material difference. Same thing with a computer here. But in reality, computers do use some fixed number of bits. So anytime you store a number or a letter in a computer, it's almost always using, say, 8 bits at a time, or 16, or 32, or 64. Generally some multiple of 2. They're conventions that we'll see. But this is precisely this same idea. Now, how, if you were given a number like, let's say, 111, how do you get from 111 to the decimal, the base 10 equivalent, just the real world expression of that number? Well, think of it how we do this in the real world. If I just let me just move my cursor over here. If you have the number like 123 in the real world, well, how does this series of digits, 1, 2, 3, translate into conceptually what we know as 123? Well, again, if you think back to grade school, this is the ones column, and this is the tens column, and this is the hundreds column. And now let me just space these out so that they all kind of line up nicely. So how do you get from 123 to what we conceptually think of as 123? Well, in the ones column we have a 3, so that's 1 times 3. In the tens column we have a 2, so that's 10 times 2. In the 100s column we have a 1, so that's 100 times 1. Add all those up, 100 plus 20 plus 3. Voila, you get this notion of 123. So now let's go back to this challenge. We kind of figured these out just by working our way up. Let's now work our way backwards. If we start with 111, how does the binary system work? Well, in the binary system, the system that computers use, we actually start with, thankfully, the ones column. But it's not the tens column that comes next, it's the twos column. And after that, it's the fours column. And so whereas in the real world of base 10 and decimal, the columns, the columns represent powers of 10. In the binary world, binary again meaning 2, it's just powers of 2. It's as simple as that. So you have the ones column, the twos columns, the fours, the 8s, 16, 32, 64, and so forth. And so now we have the ability to express numbers in just a different way. But the advantage is we don't need 0 and 1 and 2 and 3 and 4 and 5 and say all these. We don't need 10 different digits. All we need is to turn the power on or turn it off. And by doing that rapidly in sequence, we can build up some representation in electricity of numbers like this. So with that said, if I have a 1 in the fours column, a 1 in the twos column, and a 1 in the ones column, what does that now give me? 7, right? 1, 4 plus 1, 2 plus 1, 1. That gives me 7. And we can work our way up from there. So just to round this out, the reason that we often hear the term not so much bits in the real world, but bytes, megabytes, gigabytes, terabytes, and so forth, is because a single bit is actually pretty useless, certainly these days. And so somewhere along the way, the world decided that it's more useful to express units of measure in terms of 8 of these things. So 8 bits, 8 zeros and or ones, is what we call a byte. So if you had some crazy short, like MP3 or music file on your computer that was just a single byte, obviously unrealistic. They're usually millions of bytes. That would just mean there's 8 bits that compose whatever song you're very briefly listening to. And if it's 3 megabytes, that means you have 3 million bytes, or really 24 million bits if you multiply the number of bytes by 8. So when we talk about a byte's worth of bits, we have not just the 1s, the 2s, the 4s column, we have all the way up to the 128s column there. So now, a little something silly like this might make some more sense. We got through to at least one. Excellent. So if it's not quite clicking, come back to it later. But now perhaps even more comic books even will make sense. But numbers alone are not all that useful, right? You might use numbers in a computer, but more likely these days you're sending instant messages or downloading photos or reading emails and the like. So the next step up from just numbers is probably something alphabetical. The ability to express yourself as a human in English or Spanish or whatever language. You need to be able to represent other symbols using, though, at the end of the day, electricity that's on or off. Zeros or ones. Well, thankfully, the world years ago came up with a system. And this chart actually looks more overwhelming than it needs to. It's just because there's a whole lot of information. Notice that you have the same 2 columns repeated again and again. Code and char for character. Code, char, code, char, code, char. So the way to read this is that at the top left, it says the number 32. And that's a decimal number 32. And that means that the spacebar character on the keyboard is implemented inside of a computer by just storing the number 32. How do you store the number 32? We'll use some sequence of bits. Now, how do we get to the sequence of bits of 32? Well, let me just, again, come to a placeholder here. If I've got the 1s column, the 2s, the 4s, the 8s, the 16s, the 32s, I can kind of figure this out. This is the 1s column. This is the 2s column. The 4s, 8s, 16, 32, voila. If you want to represent the space bar character in something like an email or a Microsoft Word document, all the computer stores is the bit 100000. And actually, it probably uses at least a byte's worth. So this is 1, 2, 3, 4, 5, 6. So probably what it's really storing for the space bar character is 8 total bits, but the first 2 are zeros. Now, the space bar is kind of underwhelming because you can't really even see it. But if you look back at this chart and fast forward to roughly the middle of the chart, what is the code, the decimal number for the letter capital A? Yeah, it's apparently 65. And if you scroll down to the rest of the chart, the lowercase a is represented with what? 97, right? So let's do the 65. Well, 65 is also pretty easy because things line up nicely. So this is the spacebar character, which we'll represent with this, even though that's a different character altogether. The capital A then is going to have, again, 8 bits typically. 1, 2, 3, 4, 5, 6, 7, 8. But this time I need the number 65. So I have the 1s column, the 2s, the 4s, the 8s, 16s, 32s. Aha, 64, that's helpful, but I need something else. This now needs to become a 1. And so that's it. When you're hitting the letter A on your keyboard to do something completely simple like send an IM or send an email, what's really being stored in that email by your computer or in turn Gmail or the like is some sequence of bits 0, 1, 0, 0, 0, 0, 1. And what you see on the screen is the letter A. So how do these things actually get stored in reality? Well, let's see if we can't translate this idea of electricity to something that's a little more visual. Let me go ahead and open up a little demo here. And we can dim the lights just a bit, if you don't mind, for this look inside of what's been inside your computer all these years.
The hard drive is where your PC stores most of its permanent data. To do that, the data travels from RAM along with software signals that tell the hard drive how to store that data. The hard drive circuits translate those signals into voltage fluctuations. These in turn control the hard drive's moving parts, some of the few moving parts left in the modern computer. Some of the signals control a motor which spins metal-coated platters. Your data is actually stored on these platters. Other signals move the read-write heads to read or write data on the platters. This machinery is so precise that a human hair couldn't even pass between the heads and spinning platters. Yet it all works at terrific speeds.
So if you've ever wondered why dropping a laptop is generally a bad idea, it's because one of the few remaining mechanical parts inside of a laptop is, one, the hard drive, and two, the fan. And the fan is actually the cheap, easily replaceable one. This thing is a bad thing to break because obviously all of your data is on it. But we're also getting to the point, as an aside, where hard drives that spin like this are increasingly passé. In fact, a lot of you with Macs or relatively new PCs have SSDs, solid state drives. And what's nice there is that they're still electrical, but they're indeed solid in that there are no such moving parts, which means you're much safer in tossing your laptop across the room to let it land on your bed. The only thing you really risk breaking then is maybe the screen or the fan, but at least your data, with much higher probability these days, is going to be intact. Though perhaps don't try that at home. Let's dive in just a little deeper to now translate that high-level visual to the actual bits that we promised.
Let's look at what we just saw in slow motion. When a brief pulse of electricity is sent to the read-write head, it flips on a tiny electromagnet for a fraction of a second. The magnet creates a field, which changes the polarity of a tiny portion of the metal particles which coat each platter's surface. A patterned series of these tiny charged-up areas on the disk represents a single bit of data in the binary number system used by computers. Now, if the current is sent one way through the read-write head, the area is polarized in one direction. If the current is sent in the opposite direction, the polarization is reversed. How do you get data off the hard disk? Just reverse the process. So it's the particles on the disk that get the current in the read-write head moving. Put together millions of these magnetized segments and you've got a file. Now, the pieces of a single file may be scattered all over a drive's platters, kind of like the mess of papers on your desk. So a special extra file keeps track of where everything is. Don't you wish you had something like that?
So to summarize, even though we began the notion of bits with electricity, you can't always store things electrically if there's no power. And surely most of us unplug our laptops or desktops or just lose power once in a while. And it'd be nice if we not lose all of these zeros and ones. And so thus was born magnetic storage, which again, per the inside of this hard drive, stores tiny little magnetic particles that have some poles, north pole, south pole. And the idea is that you take that particle, and if you want to represent a 0, you sort of orient it this way. Or if you instead want to represent it, a 1, you flip it around so that it's south-north instead of north-south. And that there are yet other ways to represent these bits, but for now, at this point in the story, we can now just take for granted that there exists some technology or some technologies with which to represent zeros and ones and to convert high-level things like C, and as we're about to see, Scratch, into the zeros and ones that computers understand. So the program